Hello everyone, and welcome to this video titled Derivatives as Rates of Change. So in this video, I'm going to be going through a sample version, a preview version of a Knewton Alta homework assignment that is also titled Derivatives as Rates of Change. So please understand that this is a preview version of the assignment. So the questions that I'll be working on in this video may not be exactly the same as the questions that you work on when you're working on it yourself, but the objectives are the same, and the way I work on them, should be similar to the way you do things. Okay, so here we are at Knewton Alta. So we have a preview of the derivatives as rates of change assignment, which for this particular version of a calculus class I am teaching, this is section 3.4. You should see a mastery bar in the upper right hand corner. This tells you how far along you've gotten in the assignment. Next to that, an activity log, which shows you all of the objectives from the assignment. So in this particular assignment, there are the 3 objectives here that are all related to motion along a line. So then you have your current objective and a question related to that current objective. And at the bottom of every question, you should be seeing a feedback button. So you see any typographical errors in the question or the answer explanations. You can click on this, send feedback directly to Knewton support, and hopefully they can get back to you soon and help you fix whatever issue you may have. I hope it's understandable that you will not have the instructor cheat button. Right? This is for instructors only. For demonstration purposes to fill in answers. I'm not going to be using that today. But you will see a more instruction button. So if you're working on an objective or a question and you're unfamiliar with how to go about it, or you forget the material, you can click on more instruction, and then they'll provide you with some reading to do or videos to watch or both that will hopefully help you work on the questions from that particular objective. All right. So the current objective is interpret the relationship between the velocity function and the acceleration function. So this whole section of objectives is about motion on a line. We'll talk about that a little bit here first. So motion on a line. So imagine I have a number line, or I'll just draw one here. I guess you don't have to imagine it, I'm drawing it. So here's this number line. Could be horizontal, could be vertical. Okay, I'm just going to have it be horizontal here. And you know how a number line's constructed, right? You have the 0 mark. Every point on the line is going to represent some value, some real number. And you got, 1, 2, 3 values increasing going this way, -1, -2, -3 values decreasing going that way. So we're going to have a particle. Now, a lot of these problems will describe a particle or some object. Right, I'll just put object. Right, it doesn't have to be a particle. Like you're going to notice in this next question, this object will be a hummingbird. Right, so some object is moving to the right, to the left, it's moving on this line, right, or parallel to this line. So the major functions that are going to come up in these problems. So you'll see a function referred to as s of t. So s will represent the position of this object at time t, right? So the position will depend on time, be a function of time. So this is your position, on the number line. So what number are we at? What marker are we at on the number line at, time t? Now the units on position will simply be distance units. These might represent, feet, miles, inches. So units will be, feet or meters or inches or miles, some sort of distance unit. Then you'll see v of t. Right, so v of t will represent the velocity of your object. So basically how fast it's moving, but also what direction it's moving in. Talk about that in a second. At any time. So this is your velocity of the object at time t. So again, velocity here is how fast the object is moving. And this will be, the units on this. Velocity is how much the position is changing over time. So it's a position unit. So say feet divided by a time unit. So you might see feet per second or miles per hour or blah, 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 right? Something with a position unit, a distance unit in the numerator, and a time unit in the denominator. So it's how fast the object is moving and which direction. All right, so talking about direction here. So remember velocity, I mentioned it already, all right? Velocity, the way it's calculated at any particular moment, it's a change in position. So I got, delta S, how much did the position change? How many feet did I move or miles did I move? Divided by this change in time. So how fast, how far did I move over a given period of time? Now, if we want to talk about the velocity at an instant, right, we take the limit as delta t approaches 0, right? Have that change in time shrink to nothing and be at 1 instant. So this may look familiar as the derivative, right? This is ds over dt, the derivative of s with respect to t. How fast is the position changing at that time? You know. So velocity is just s prime, right? Velocity at a given time. It's the derivative of the position function. So again, s prime of t or ds over dt, same thing. Now, think about how the object's moving. If we're moving to the right, So say moving to the right. We're talking about which direction. Or from left to right. So a little arrow here. If you move to the right on the number line, the value of the position will be increasing. So you may recall that the derivative, right, the first derivative, if a function is increasing, right, if a function is going up, the derivative is positive. Right, that came up before. So when you're moving to the right, right, when this object's moving to the right, the position value, the s value is increasing, meaning that s prime, or the velocity, must be positive. Okay, so velocity greater than 0, right? Velocity positive means the object is moving to the right at that time. All right, then the other way around, moving to the left. That's going the other direction, right? So going this way from right to left. Now, if you're an object on the number line here and you're moving to the left, the position you are at, the S value, is going down. It's decreasing. Again, you may recall that when a value of a function is decreasing, it's lowering. The derivative is negative at those places. So S prime will be negative when the object is moving to the left. Or the velocity will be negative, less than 0, when the object is moving to the left. And then you'll see these words as well. If an object is at rest, okay, the words at rest, that simply means at that moment the object is neither moving right or left. It's at a standstill. It's at rest. So that's where your velocity is equal to 0. All right. Okay, then we also have acceleration function mentioned. So again, the velocity function is the derivative of the position function, and the units on it will be, position units over time units. All right, then we have the acceleration function. I'll keep the same picture up, put up a little bit. So then you'll see this a of t. So again, this is the acceleration of the object at time t. And you may recall from well, I don't know what else you've taken before, but so here it is. The acceleration is a measure of how much the velocity is changing over time. So I would take the change in velocity, delta v, how much did my velocity change, divided by how much time went by. So delta v divided by delta t. But then if we want to make that at one instant, at one particular time, we take delta t and have it approach 0. So our acceleration at any particular time is simply, again, hopefully this looks familiar, the derivative of the velocity function, dv over dt, or v prime. All right, so the acceleration of an object at any given time is the derivative of the velocity, which I guess you could also say was the second derivative of the position. Throw that on here. is, oh, I'm sorry, throw that down here, equals s double prime, right? Because remember the first derivative of position was velocity, and then if I do the derivative again, I'd get acceleration. So you could say the second derivative of position was acceleration as well. Now the units on these, right, the units on acceleration, and it's a change in velocity. So you have velocity units in the numerator over a change in time. So it's like feet per second in the numerator, per second again. But instead of writing all that, typically it's feet per second squared, right? Because you have the second in the denominator here, second squared. So you'll see feet per second squared. I could have miles per hour squared, right? So whatever the time unit is, has this square on it when you're writing acceleration units. Now I like to think of acceleration as being pulled in a certain direction. Right? So your object, it may be moving to the left, but some force is pushing it in the right direction. I may be moving left, but some force like a wind, think of wind. If I'm moving left and the wind is blowing the other way, that would be slowing me down, pulling me toward the right. Even though an object may be moving left, some force may be pulling it to the right, and vice versa. An object may be moving to the right, but again, think of wind or water or gravity, in some direction or another, but something may be pulling it in the opposite direction. Or I could be moving right and being pulled to the right, or moving left and being pulled to the left. But acceleration is a pull. Think of acceleration as being pulled in one direction or another. So being pulled in the right direction on the number line, or to the right. So my force is going this way. So again, this is like the wind is blowing this way, the water is flowing this way. You might be moving against it, but you also might be moving with it. But either way, there's a force, something pushing me toward the right. So this is when your acceleration will be positive. Because again, think about what happens here. If I'm moving left, say I'm moving toward the left, but there's a push to the right, the velocity would be negative, but I'd be slowing down, right? So the magnitude of the velocity, your speed, would be getting smaller and smaller, right? You'd be slowing down. So going from a negative velocity up into a point where the force is so strong you stop. Well, if you're going from negative velocity to like a zero velocity and then you start being pushed to the right, get a positive velocity, that means velocity is increasing, right? So the v prime, which is acceleration, would be positive, right? So velocity is increasing in this case. Now, if the force is pushing you or pulling you to the left, all right, I'll say to the left this time, in the left direction, to the left. So again, think of the water flowing to the left. So again, what's going to happen here is if I'm moving right, that means I got a positive velocity. This pushes me to eventually have a oh, sorry. So if I'm moving to the right with a positive, again, moving right means positive velocity, but this force is pushing me so that I eventually move left, that means I'm going from a positive velocity to a negative velocity. So velocity is decreasing. And if velocity is decreasing, that means the derivative of velocity would be negative. So acceleration is negative in these cases when you're being pulled to the left. There's some force pushing you or pulling you toward the left direction on the number line. Okay. All right, and then a couple other things before we actually get into a question. So they talk about the relationship between these, right? This first objective I'm looking at is the relationship between acceleration and velocity. Oh, and I guess too, speed is another thing you'll be asked for. Speed is simply the absolute value of velocity. Oh, sorry, absolute value, not just one bar, just one bar. So whatever your velocity is at any given time, just make it positive, right? So if I have a negative 3 feet per second velocity, the speed would be positive 3 feet per second. So whatever the velocity is, just make it positive, make it non-negative, and that's your speed. So now the relationship between velocity and acceleration. So one is when these have the same sign. So when velocity and acceleration have the same sign, that means, both positive or both negative, both plus or both minus. Then the object, the speed of the object will be increasing. The object speeds up, gets faster. Oh, sorry, speeds up. Right, I was saying gets faster and wrote the word faster, but the object speeds up in this case, right? So again, let's throw some colors in here. So again, say my velocity is positive. So again, if v is positive, that means I'm moving to the right. And if the acceleration is positive, there's acceleration, it's pushing me that way as well. So I'm moving this way and getting pushed more that way, right? So the object will go faster in that direction. Same thing with if they're both negative. If my velocity is negative, that means the object's moving left. And if the acceleration's negative, that means the pull or the push is also going left. So the object's moving to the left and it's getting pushed that way too. So that makes it even faster. It's like going with the wind or with the water, when you're rowing or something. And then of course the other way around is if these two things, when the velocity and acceleration have opposite signs. Right, so that means one's positive and the other's negative. This is like going against the wind or against the water. So for instance, say velocity was positive, so the object's moving right, but acceleration's negative. Well, if I'm moving to the right and something's pushing against me, I'm slowing down. Right? When velocity and acceleration have opposite signs, they'll say the object, slows down. The speed of the object would decrease. But the object slows down in that case. So again, that's when velocity is positive and acceleration is negative, or if velocity were negative, so the object's moving left, but the acceleration's positive. So again, that means some force is pushing you to the right. So if object's moving left, but something's, you're going against the wind, against the current, against the water. Something's pushing against you, so slowing you down. All right, so let's point out all those relationships, and again, how when you're given a position function, the derivative is velocity, and then the derivative of velocity is acceleration. And then you got this as well, the slow down, speed up info. All right, so after all that, finally, all right, back to our question here. It says, the position of a hummingbird flying along a straight line is given by this function here. So S of t, the position of the bird at time t, right? What number it's at on the line. What yard marker, right? So this will be in yards. It's t cubed over 3 minus 5t squared plus 24t plus 2. Where t is non-negative, right? So no negative time is being discussed here. And time is measured in seconds. And S, right, the position is in yards. So on what interval or intervals is the hummingbird speeding up? And we're asked to enter our answer in interval notation. Now, when they say on what intervals, they're talking about time intervals, right? Just like intervals of the input. So at what times, at what values of t will this hummingbird be speeding up? So I just went over talking about that, right? So we got the position of this bird on this line at any given time is given by, it was t cubed divided by 3. I'm going to write it this way, 1/3 t cubed minus 5t squared plus 24t plus 2. And then again, they mentioned that they don't want to talk about any negative time. So time is greater than or equal to 0. So we're asked, for what values of t on what intervals of time is the bird, right, the object in this case is a bird, speeding up. So remember I said this before on the previous page that I had up before we started the problem. These objects will be speeding up. Speed, how fast they're going, will be increasing if they're moving in the same direction that they're being pulled, right? If you're moving with the wind or with the water. So this is, again, where velocity and acceleration, v of t and a of t, have the same sign, right? They're both positive or both negative. So we're looking for values of t that make this happen. So I need to know my velocity and acceleration functions. So remember, velocity is this the derivative of the position function, over time with respect to time. So treat t like you would x, earlier with polynomials and stuff. So I'm just going to do power rule and whatnot term by term here. So first term would be 1/3 times 3t squared. So that's just t squared. Then minus 5 times 2t, so minus 10t. And then plus 24. All right, and then plus, 0. So there's my velocity function. And again, position would be in yards, right? So for any given time, it would tell me what yard marker I'm at on the number line. Velocity would be in yards per second, because again, it's going to be position over time, change in position over change in time, and time was in seconds in this problem. And then my acceleration function. And the acceleration function is simply the derivative of the velocity function. So I'm going to do it again, go term by term here, power rule. You got 2t to the first minus 10. Okay, and then the units on this would be in yards per second per second. So yards per second squared, right? Square the time unit. So change in velocity over change in time. Okay. So here's how I like to approach these. So I'm going to make a number line, two of them. One where, again, the number line will represent different times. So this isn't representing position. All right, this is a timeline right now. And we're only looking at times, bigger than 0. So I'm going to have 0 be at the left here, greater than or equal to 0. So again, these are all non-negative times. And then I'll have one for the velocity. I'm going to do the same thing for acceleration. I'm going to try to line these up perfectly. All right, so 0 at the far left here. Again, we're only looking at non-negative time. And this is more time here, and then you got acceleration. Right, so this will be my velocity timeline. How, what direction, this will tell me what direction the bird is moving in, to the right or to the left on the line at any given moment. And then acceleration, an acceleration timeline, which will give me an indication as to which way the wind's blowing, which way the forces are pulling at the bird at any given moment. So what we want to figure out is, where velocity and acceleration are both positive or both negative. So I'd like to indicate on the timeline where the velocity is, positive, negative, or 0, or undefined even. Right? Those are your only four options when you evaluate an expression. You're either positive or negative or 0 or undefined. So this velocity function, this is a nice factorable quadratic, right? This would factor to t minus 4 times t minus 6. So you see at t equals 4, so 4 seconds, right? So again, my time is 4. The velocity would be 0. That would be at rest, right? Again, when the velocity is 0, we'll say the object is at rest. So this bird is, neither moving to the left nor to the right at the 4-second mark, right? 4 seconds into their flight. Also for 6 seconds, so 2 seconds. So then it starts moving again, and 2 seconds after that, it's back at rest. It's got another velocity of 0 yards per second. So the velocity is 0 at 4 seconds. The velocity is 0 yards per second at 6 seconds. And then I plug in other values of time here, because I know where the velocity is 0, and it's a polynomial, so it'll never be undefined. So for all these other times, from 0 to 4, between 4 and 6, to the right of 6, it's going to either be positive or negative. Now if I plug in a time to the left of 4 here, say 0, see how velocity would be positive 24? So there'd be positive, I'll put little plus signs here. There's going to be positive velocities, meaning this bird is moving to the right on this line for the first 4 seconds. And then 4 seconds, it's stopping at that instant. It's not moving at that one moment. And then between 4 and 6, and say I plugged in 5. Now 5 minus 4 is 1, times 5 minus 6 is negative 1. 1 times negative 1 is negative 1. You have negative velocities. So I'm going to put little minus signs here. So there are negative velocities between 4 seconds and 6 seconds. Again, this means that from 4 seconds to 6 seconds, now the bird is moving to the left on this linear path it's on. And then plug in a time beyond 6 seconds to my velocity function, say 7 or 8. You have a positive factor, a positive factor. This would be a positive overall value. So I'm going to put little plus signs here. So again, after 6 seconds, so again, the stops moving left for an instant, got a 0 velocity at 6 seconds, and then after that, it turns around, starts moving right, starts flying to the right on this linear path. So moving right for the first 4 seconds, pause, left for the next 2 seconds, pause, and then right, the rest of the time after 6 seconds. All right, and I'm going to do what I just did here with velocity for the acceleration function as well. So this is another one that's easy to tell that what makes it 0, right? This is 2 times t minus 5, or if you were to set this equal to 0, add 10 divided by 2. Now, I'm going to try to line these up perfectly. So 5 seconds is in between 4 and 6. So I'm going to put this here, right beneath, where 5 should be up there. So there's 5 seconds. And at the 5-second mark, the acceleration is 0 yards per second or yards per second squared. There is no pull, there is no, it's like a standstill, no wind, no water pushing you in any direction at that moment only. So then at every other time, again, because this is a polynomial, it's not undefined anywhere, right? So like every other time is going to give me either a positive acceleration or a negative acceleration. Well, to the left of 5 here, if I were to plug in 0 or 1 or 2, this would be a negative number, right? So we have a negative acceleration. Put little minus signs here. We have a negative acceleration for the first 5 seconds. So that means when this bird's flying, for the first 5 seconds, the wind is blowing to the left. The water, I'll say the wind because it's flying, but the wind would be blowing to the left. So look, see in the first 4 seconds, the bird is flying to the right, the wind is blowing to the left. So in the first 4 seconds, the velocity and acceleration have opposite signs. So in these first 4 seconds, the bird is slowing down, and that's not what we want. We're asked, where is the bird, speeding up. But look from 4 to 5 seconds, right? So here's 4, there's 5 up here. So look from 4 to 5 seconds. In that next second, the wind is still blowing to the left. But now the bird has turned around and is also moving to the left. So the wind is blowing left and the bird is moving left, negative velocity. So moving with the wind, speeding up. So that's going to be an answer. We'll write in a minute. And then to the right of 5 seconds, so again, the acceleration is 0 at 5 seconds. Plug in a time bigger than 5 seconds, and this is going to be a positive value, this acceleration function. Plug in 6, you'd get 2. Plug in, 10, you'd get 10. So positives here. So now, so it's like the wind is blowing to the left for the first 5 seconds. Then it stops blowing for an instant and turns suddenly, and turns around, and now from after the 5-second mark, so 5 seconds onward, I'm just going to line the 6 up here. The wind is blowing to the right. So look. So again, we go left to right. Like I said, the first 4 seconds, velocity and acceleration have opposite signs. So the bird is going against the wind, getting slowed down. All right, so I'll highlight that here. First 4 seconds, bird is getting slowed down. But then from 4 to 5 seconds, right, just in that next 1 second, the bird's moving left now. It's got a negative velocity. And the wind is also blowing to the left. It's being pulled left. So going with the wind, sped up. So the bird is speeding up in that single second. But then the wind changes direction, right? So from 5 to 6 seconds here, the wind changes direction. The pull is now to the right. Wind is blowing right. but the bird's still moving to the left, still got a negative velocity. So opposite signs, the bird is slowing down in that 5 to 6 second time. And then for the rest of time, right, the rest of the time of this bird's flight, from 6 seconds onward, now the bird is turned and moving right, got a positive velocity. The wind is also blowing to the right, the pull is to the right. So the bird is from 6 seconds onward going with the wind, meaning it's being sped up. So our answer, they ask us for intervals here, interval notation. So I'll write it down here. The bird is speeding up on intervals. And again, it's got to be interval notation. So remember the from 4 to 5 seconds. So 4 comma 5, but parentheses on those though. Because again, at 4 and at 5, velocity is neither positive. At 4, the velocity is not positive or negative. At 5, the acceleration is not positive or negative. So you can't talk about them having the opposite sign. So just parentheses on these ends, 4 to 5. And then you got the union symbol. Right, it says if there's more than one interval, write the intervals as a union. Remember this little union symbol to break up the gap between intervals. Kind of represents the word or. Now again, 5 to 6 seconds, slowing down, and then beyond 6 seconds. So from 6 seconds forever, right? It's from 6 to infinity for the rest of the flight. Say this bird flies forever. It's kind of silly, but it's kind of what's being indicated here. Speeding up, going with the wind, moving to the right, and the wind is also blowing. The pull is also to the right. So here's what I'm going to answer in interval notation. So you're just entering intervals down here. So again, parentheses 4 comma 5, and then that union symbol, which is here in the sets in the keyboard, and then parentheses 6 comma, infinity should be in the keyboard somewhere. All right, I don't see it here, so maybe you can drop down the keyboard, go back to some other version, and I see infinity here in the keyboard, another keyboard menu. And there, for those intervals of time, the bird would be speeding up. All right, when you get something correct, it'll give you a green banner and some encouraging words, telling you that you're right. When you get something incorrect, sometimes if it's like a fill in the blank like this, they might give you another chance. But if you get that second chance wrong, or just, multiple choice, you get it wrong for the first time. Anyway, you get something wrong, you'll see a red banner with still some encouraging words, like, hey, almost, nice, keep trying and stuff like that. And then after, you'll see an answer explanation. I would recommend reading through these, whether you get it right or wrong. If you get it correct, maybe you did it in a different way than they did it, and you like the way they did it better. And you might want to do their method, the next time you see a problem similar to that. I would definitely read through these, though, these answer explanations if you get something wrong, right? Because hopefully you can see where you made your mistakes and learn from them for the next time you see a problem like that. All right. So again, they're doing the whole number line thing like I mentioned. All right, so now we're on the objective, simply find the acceleration function given a position function. So remember very simply, the acceleration function is the second derivative of the position function, right? So s of t is given here. So I'll write this out. It's the first one from this objective. So yeah, our position at any given time is given by this function, this expression 2t to the fourth minus 2t cubed minus 2t squared, then minus 8. And yeah, they ask us for the acceleration function, and this is in meters, they said, right? This is in meters, and time is in seconds. I mean, it doesn't really matter here. They just want the expression for the acceleration, but still, I'll talk about the units as well. So remember velocity. The velocity function is, just the first derivative of position. And this is a simple polynomial here, just going term by term and applying the power rule. 2 times 4t cubed would be 8t to the third, then minus, 6t squared, then minus 4t to the first, and then, plus nothing. The last term is a constant. Now the units on the velocity, though, would be meters per second, because again, velocity is a change in position over a change in time. And then the acceleration function that they're asking for, again, you can write this a couple ways. It's the first derivative of velocity or the second derivative s double prime of position. So again, velocity here, another simple polynomial, just going term by term, applying the power rule. So you'd have 24t squared minus 12t to the first, and then minus 4. This is what they want us to enter, just the expression that would give us our accelerations. Now they don't have the units there. You don't have to type the units in, but the units on the accelerations in this case would be meters per second per second. So meters per second squared, right? Always is squaring the time unit. It's a change in velocity over change in time. So, but still, I'm entering what I bubbled in here in the blank. And that is all that's being asked for. Okay, so this 24t squared minus 12t minus 4. Great. Okay, so pretty quick one there. So back to this one with the speeding up. Now this time it is a car, instead of a bird. But still, some object is moving along a straight line, right? So this highway is supposed to be a straight line, a motion on a line. And, the position is in meters. So, when I plug in a value for time, it'll tell me at what meter mark of the highway I'm at. And then velocity, time is in seconds. So velocity would be in meters per second. And acceleration would be in meters per second, or meters per, square second, right? Second squared. All right, so like the first question from this objective we did, I'm going to write this out. It's another nice polynomial one. All right, so shouldn't be too hard to find the derivative and then also determine where values are positive or negative or 0. And because they're polynomials, right, the value will never be undefined. So here the position of this car on this straight highway is given by negative, the opposite of t squared, -1 times t cubed, plus, then the coefficient of the next term is 9/2, 9/2 times t squared, plus 12t to the first, and then minus 5. And once again, they're only having us consider, non-negative time, t is greater than or equal to 0. And then, yeah, where is the car? Right, so where is the car speeding up? Once again. So same thing as the first question I went over like this, right? Speeding up means that the velocity and acceleration have the same sign. So they're both positive or they're both negative. right? It's like, again, it's like going with the wind, moving to the right and being pushed to the right by the wind, or moving to the left and also being pushed to the left by the wind, right? They have the same sign. So we need to look at velocity, right? So again, velocity, the first derivative of our position function here. So this would be negative, 3t squared, plus then 9/2 times 2 would just be 9, right? So plus 9t to the first, and then plus 12. Then our acceleration function would be the derivative of that, right? So negative 6t to the first plus 9. Okay, and that's it for that. Now I think it's easy to see where the velocity is 0. Now you can set this equal to 0 and use the quadratic formula or whatever. Same thing down here. You can set this equal to 0 and figure out where the acceleration 0 is solved. But these are nice and factorable, so it should be easy to see where the acceleration and velocity are 0 by looking at the factors, right? This one, you could pull out a -3, right? Usually when the lead is negative, you factor out a negative. And then you'd have t squared minus 3t minus 4. And so we have -3 times, and then this t squared minus 3t minus 4. That would factor to t minus 4 times t plus 1. And so when I go to make a number line, right, now this is a timeline though, this is not my position line like on the highway. All right, but this will give me a timeline that will tell me, what the velocity of the car is at any given moment. So if it's positive, the car is moving to the right on the highway. If it's negative, the car is moving to the left, turned around and moved to the left, or backing up on the highway. And again, we don't really want anything less than 0 here, right? So I'm going to have this number line here start at 0 and only be positive after that. So I already said, right, you look at these factors. So the times where the velocity is 0, so the times where this car is at rest, one of them would have to be at 4 seconds. So here's 4, and the velocity is 0 at that time. Now the velocity is also 0 at -1, right? T equals -1. Velocity at -1 would be 0. But I already mentioned, right? We only want non-negative times, right? So -1, I'm not going to worry about that one. Only 4 seconds. So at 4 seconds, the car is at rest. It is stopped for a moment. Now we care about, these times to the left of 4 and to the right of 4, and if the velocity is positive or negative. So to the left of 4, again, you can plug in 0, 1, 2, 3 to my velocity here. Well, 0 would be nice. If t were 0, clearly you got a positive velocity. The value would be positive 12. All right, so I'll put little pluses there. So from the beginning of the drive, for the first 4 seconds, this car is moving to the right on the highway, this straight line highway. Then it stops for a moment. And after 4 seconds, plug in 5, 6, 7, plug in a million. This would clearly be negative, right? This first term would be huge negative. So we'd have, or you can go the factored version here. Plug in 5, you'd have 1 times 6 times -3, which would be negative, right? So you have negative velocities after 4 seconds forever. So for the first 4 seconds, the car is moving, to the right on this highway, and then stops and then backs up and is moving left for the rest of time. Right, and then the acceleration, again, same thing here. I can pull out a -3 from this, and then we'd have 2t minus 3, and you can hopefully see it, or again, it wouldn't be tough to set this equal to 0 and see that you get 9/6 or 3/2. Right, the acceleration at 3/2 would be 0, 1 and 2 seconds. So I'm going to line these up nicely. So again, this is another timeline, but this time for the acceleration of the car at any given moment. Now 3/2, 1.5 second would be here. So I'll do that here and line it up here. So here's 3/2, 1.5 seconds. And again, we want this to start at 0, no negative times. So I got no acceleration, right? So again, the wind, or again, think of the wind pushing you in one direction or another, pulling you one way or another. I'll also line up the 4 down here. But still, at 1.5 seconds, no acceleration. So everywhere else, it's going to be either positive acceleration or negative acceleration. Now, when time is 0, acceleration would be +9. So positive accelerations for the first 1.5 seconds. So again, like the bird problem from earlier, you see in this first 1.5 seconds, the car is moving to the right and the wind is blowing to the right, or being pushing to the right. So they got the same sign. You're going with the wind. So you are being sped up. The car is speeding up in those first 1.5 seconds. Now, for the rest of time, and you could talk about the 4 seconds here. Well, actually, we should stop at 4 because that's where velocity is 0. So from 1.5 seconds to 4 seconds, again, if I were to plug in 4 or anything to the right of 3/2 here, this would be a negative number. Acceleration's negative after 3/2, so it's negative the rest of the time. So after 1.5 seconds, the wind goes from blowing to the right to blowing to the left. But you see this, if you compare the velocity and acceleration here, between 1.5 seconds and 4 seconds, see the velocity is positive, so the car is moving to the right still, but now the wind's blowing the other way against the car, so you'd be slowing down. But then from 4 seconds onward, see at 4 seconds the car stops at rest, and then it starts moving left again, and that's with the wind. Cars moving left, wind's going left. So being sped up again, right? The velocity and acceleration have the same sign. So once again, there are 2 intervals here. So the car speeds up on these time intervals. So one of them was from 0 to 1.5 or 3/2 seconds. Now at 0, this time I'll use a bracket, because look, at 0, velocity would be +12, and the acceleration would be +9, meters per second squared, and velocity is +12 meters per second. They're both positive at time 0. So bracket, right? 0 is a time where the car would be speeding up. 0 is a time where the velocity and acceleration have the same sign. So again, I'm using a bracket on that, not parentheses. 3/2, the velocity is positive, but the acceleration is 0, which is neither positive nor negative. So they don't have they don't have the same sign or opposite signs there. So I'm not going to include 3/2, parentheses on 3/2 seconds. But then there was this other one, right? Again, union. And then from 4 seconds onward, right? From 4 to infinity, 4 seconds onward, going left, and the wind's blowing left as well, right? You're going with the wind, getting sped up. They have the same sign. Now at 4 seconds, the acceleration is negative, but the velocity is 0. That's neither positive nor negative. So parentheses on that, and you always have parentheses on the infinities. Right? So there's what I'm going to be entering. Right? The intervals of time for which this car would be speeding up, would be getting faster in whatever direction. So yeah, my first interval, right, was again bracket, right, 0, comma, and then 3/2, right, and then parentheses after that. Then that union symbol, which I'm seeing here, and then parentheses, from 4 seconds onward, 4, 2, and then go to the basic keyboard to find infinity. And then the parentheses are already there on infinity. That's great. So anytime the velocity and acceleration have the same sign, you are speeding up. Let me go through all that here. All right. So now it's just simply find the velocity function given the position function. So these should, now notice they got the units on this one, right? It's feet per second. A velocity, change in position over change in time, feet per second. So you're just entering a number here, it looks like. So look, a projectile is fired vertically, upward with a velocity of 160 feet per second. So its position function can be modeled. So this is like height off the ground, straight off the ground. So its height off the ground, given as s of t equals negative 16t squared plus 160t. Where position s is in feet and time is in seconds, right? Because the velocity is given in feet per second. They're saying, what is the velocity of the projectile when it first reaches a vertical height of 144 feet, right? Because it would go up, be 144 feet in the air. Maybe it goes a little higher, but then it eventually falls back down. And while it's falling, it'll be 144 feet in the air again at some point. All right, so they're saying when it first reaches, so on the way up. All right, so on the way up, when does it hit the 144-foot mark off the ground? So we're given this position function, right? So the height of the object off the ground here is given by negative 16 p squared plus, 160 t. So first I'm gonna find when those happen. I'm gonna find t, find the times for which our height is 144 feet. Right? So at what times, so then this object's going up and then it's coming down. Right? It's going up and then it's coming down. And at some point, it's 144 feet in the air. Well, again, we want that first one, right? There's maybe one time and then it goes up higher and then it comes back down. There's another time. So I just want to find what those times are. So we're solving this equation, right? Where is our position 144 feet? So that's negative 16, t squared plus 160t. And, again, when is this equal to 144? So I'm going to take everything to one side, add, so we have 0 equals positive 16t squared, and then minus 160t, and then, still have the plus 144 over there. Let's see, that's 4t squared, that's 12 squared. Yeah, I could factor this a little bit, see if anything comes out of this, Oh, this is a multiple. This is 9 times 16. All right, 144. This is 10 times 16. This is 16 times 1. So I can factor out 16. And then you have t squared minus 10t plus 9. And yeah, there's 16 times and then t minus 9 times t minus 1. So yeah, the solutions here equals 0. Of course, I got equals 0. So 1 second or 9 seconds are my answers to that question, right? Um, so this thing gets shot up in the air. So after 1 second, it'll be 144 feet in the air, and then it goes higher, 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 and then 8 seconds later, at the 9-second mark, 9 seconds after it was shot, it's back at 144 feet when it's falling down. So this is the one we concern with, right? So this is the first time it's 144 feet in the air at 1 second. So they want us to find the velocity of this object at this time. So remember, velocity is the derivative of position. So this nice little polynomial one again, that'd be negative 32t and then just plus 160. And at this time, the velocity at 1 second would simply be negative 32 times 1 plus 160. So that's negative 32, plus 160. It's positive 128, feet per second is what the units are on that. But that's what they're asking for. This is what I'm going to fill in the blank. What is the velocity of this? Now we'll consider going up positive and down negative. So this means, I'm still going up at this speed, right? I'm going up at a rate of 120 feet per second at that moment, right? At 1 second after the thing was shot into the air. So yeah, so here's just positive 128 feet per second. So another one with the velocity function given the position function. All right, so this is another hummingbird flying along a straight line path. The position in yards, is given by this function here, this polynomial. The position that the bird is at, the yard marker that it is at any given time is given by this, and time is in seconds. So at what time or times with, non-negative time again, so no negative answers. At what time is the hummingbird at rest? And separate multiple answers with commas, right? So t, they have the t equals already. You're just putting in the seconds, you're just putting in the numbers. So remember, at rest meant the velocity is 0. So again, our position function is given as negative 2/3 times t cubed plus, 2 times t squared plus 48t. So again, at rest, they want to know at what times is this bird at rest, right? That once again means velocity is 0. Here that would be 0 feet per second. Nope, yards per second. Sorry, yards per second. So solving this, well, the velocity function again is just the derivative of the position function. So that'd be negative 2t squared, and then plus 4t to the first, and then plus 48. And we're setting that equal to 0. All right, so when is negative 2t squared plus 4t plus 48, when is this equal to 0? And I'm hoping, based on previous problems, that we can just factor this again. Now I could, you could just, because it's a quadratic, you could jump into the quadratic formula here, but if I factor out a negative, all these have a factor of 2, and factor out a negative 2 because it has a negative lead. We'd have 2 squared minus 2t minus 24. And this t squared minus 2t minus 24 factors to t minus 6 times t plus 4. And so our solutions to this are, t equals 6 seconds or t equals, negative 4 seconds. But, they mentioned that we only want non-negative time. Okay, so this negative value of time that works is not going to be considered correct. So at 6 seconds. All right, so this bird, 6 seconds into its flight will pause for a moment, will be at rest, have a velocity of 0. So yeah, just 6. If there were more times, though, I would put a comma, and then the other values. All right. So another acceleration function. So this is find the acceleration at a particular time, though. So notice those ones where you're plugging in a particular value, they actually have the units there for you already. So you see this is an acceleration, so it's meters per second squared, right? You got the square time units. Change in velocity over change in time, meters per second per second. All right, so the position, it's another car moving down a straight line highway, right? Car along a highway. Its position, the meter mark that it's at any given time is given by this polynomial here, and t is in seconds. Find the acceleration of the car, which way is it being blown by the wind, which direction is the wind going, kind of, if you think of it that way, which way is it being pulled at 2 seconds. So yeah, this is, again, hopefully no problem now with polynomials. So position 2t to the fourth minus 10t cubed minus 5t squared plus 9. Yeah, and we want the acceleration at 2 seconds, right? 2 seconds into this car's drive. So I need to go a couple derivatives here, right? Velocity is next. It's the first derivative of the position, so that'd be 8t cubed minus 30t squared, and then minus 10t, plus 0. And then the acceleration at any given moment would be, again, the derivative of velocity, or the second derivative of position. So 24t squared minus 60t, then minus 10. So at 2 seconds, right, I'm just plugging 2 in. So a of 2 be 24 times 2 squared minus 60 times 2 minus 10. 2 squared is 4. 4 times 24 is 96. So that's 96 for the first term, then minus 120, for the second term, minus 10. So it's 96 minus 130. So this would have a negative velocity. That'd be negative 34. And that's, meters per second squared, right? But negative 34 is what I'm entering. And don't forget the negative, right? So this means at that time, the wind, the acceleration, the way it's being pushed or pulled is to the left. It's negative. So I'm just entering that in the box here, negative 34, meters per second squared. So another velocity. Now this one, yeah, it says on what interval. So you're given a position function, right? Some particle, this time not a bird or a car. So a particle, is traveling along a horizontal line, a number line, according to this function, right? So the position, the feet mark or the foot mark it is at any given time is given by this polynomial here for, again, non-negative time, and t is in seconds. On what interval or intervals is the particle moving to the left? So remember, on the horizontal number line, like on my picture, way earlier in the video, moving to the left means the position value, the value of s, is decreasing. So s prime, or the velocity, would be negative, right? So we're looking here for what times would this particle have a negative velocity. So here's our position function. So again, it's negative 2/3 times t cubed plus 4t squared minus 6t minus 3. Once again, t is non-negative times. So yeah, the velocity function is just the first derivative. So negative 2, t squared plus 8t, then minus 6. And then they're asking us about, again, when is the thing moving to the left on this line? So we're looking for where is the velocity, less than zero? Where is the velocity negative? So like I was doing before with our speeding up questions, where's the bird speeding up or slowing down or whatever? I'm gonna make a number line here. This is a time line. This is not the position line, right? This is a time line starting at zero, no negative times, for the velocity. Now, if I were to factor this, right, you got -2 times t squared minus 4t plus 3. And this is -2 times, t minus 3 times t minus 1. Or sorry. Yeah, t minus 3, t minus 1. So there are two times here, 1 second and 3 seconds. Put those down here where the velocity is 0. So those are the times for which this particle will be paused, at rest, stopped for a moment. So at every other time, because this is a polynomial, it's either going to be positive or negative, right? It's never undefined. So to the left of 1 here, well, when the time is 0, the velocity at 0 is negative. So I have negative velocity, for the first second. And then from 1 to 3 seconds, plug in 2 or something. This would be, if I go in the factored form here, that's negative, positive, negative. So a positive overall. So I have positive velocities between 1 and 3 seconds, and then to the right of 3, negative again. All right, you can plug in a million, a billion to see that this is definitely going to be a negative value. Or plug in 4 and you can see it's negative. So in this first second, particle's moving left. It's got a negative velocity. So position would be decreasing, position numbers are going left, lowering. Between 1 and 3 seconds, that's where the particle would be moving to the right. Okay, there's a positive velocity, so the position values would be going up, increasing. Positive velocity, positive derivative. And then after 3 seconds, 3 seconds onward here, we're back to moving left. Okay, the velocity is negative once more. So there are two intervals that we're going to answer here. So the intervals where this particle would be moving to the left are where you have a negative velocity. So that's from 0 to 1. Again, I'd put a bracket on the 0, sorry, because at 0, the velocity is negative. So it's included. But at 1, I'll put a parenthesis, right? The velocity is 0 there. It's at rest. It's not technically moving in either direction at that moment. Right? So not moving, I'm not going to say it's moving left there. So 0 bracket, because you do have a negative velocity. 1 parentheses, because again, the velocity is 0, but everything in between, it's a negative. And then you got the union. And then this interval here from 3 to infinity, right? 3 seconds onward, negative velocity, the particle will be moving to the left. Parentheses on the 3, right? The velocity is 0. It's at rest. It's not moving left at 3. And you always have, infinity parentheses on the infinities. So here's what I'm going to be entering for the answer to this question. So bracket, 0, comma 1, parentheses, and then that union symbol once more. And then from 3 to infinity, and that's in the basic keyboard. And the parentheses are already there. How nice. Great. So this is pretty similar to a question we had earlier. Again, some object is launched into the air with some initial velocity. They give us the position function, how high it is off the ground at any given time. And, we want to know the velocity when it first reaches the height of 880 feet in the air. So like that problem earlier, right? It might be shot up, hit 880 feet and then go a little higher, and then on the way back down, be 880 feet in the air again. All right, so we got to figure out first I'll figure out what times is this object, this ball, 880 feet in the air. So I'm going to have set the position to be 880. So again, the position that this ball, the height off the ground, how high the ball is off the ground is given by this, negative 16t squared plus, 256t, and this is in feet. Right. Yeah, so we're solving this first. Right? When is this happening? Right? For what values of time is the position, 880 feet off the ground? So we have this negative 16 t squared plus 256 t equals 880. Again, I can move everything. I like having a positive lead coefficient, so I'm gonna move everything to the right. You can switch sides if you want to keep it on the left, but so I have 0 equals 16t squared, then minus 256t, and then I still have this positive 880 over here. And yeah, I think like last time, I think 16 goes in all these. This is 16 times 1. This is 16 squared. And this is 16 times 55. Yeah. Yeah, because that'd be 88 times 10. And then this is 8 times 11. This is 5 times 2. Yeah, so you got the 16 and the 55 with the 5 and 11, right? So if I got 0 equals, factor 16 out, you got t squared minus, 16t, and then plus 55, and then factors of, this factors the t minus 5 times t minus 11. So at t equals 5 seconds and t equals 11 seconds, this particle, this ball, would be 880 feet in the air. And they asked specifically for the velocity at the first time, right? So the earliest time that it hit 880 feet in the air. So that's at 5 seconds. All right, so we want the velocity there. Now the velocity at any time, again, just the derivative. So negative 32 p plus, 256. And then the velocity of this ball at 5 seconds is, negative 32 times 5 plus 256. This is 160, negative 160 plus 256. That's 96, positive 96, feet per second. And they already have the feet per second. You don't have to type that, right? You just type in the number. And being positive means, again, it's still going up, right? Going up where the height is increasing, right? So the derivative would be positive. So it's going up at a speed of 96, feet per second at that moment when it first hits 880 feet off the ground. All right, so that objective with the velocity function is done, just plain velocity. All right, so now acceleration. Again, very similar to a problem earlier. We're given our position of this car moving along a straight highway and asked to find the acceleration of the vehicle and which way it's being pulled or the wind's blowing against it or with it, which way the wind's blowing, the acceleration, which way the pull is going at 2 seconds. So again, the position given by this polynomial, 2t to the fourth minus 9t cubed minus 6t squared minus 8 And this is in meters here. And then the velocities in meters per second, and accelerations in meters per second squared. All right, so velocity, derivative of this, so 8t cubed minus 27t squared minus 12t, and then the acceleration function, so again, that would be in meters per second. Meters per second squared for acceleration, which is, derivative of velocity. So 24t squared minus 54t, then minus 12. And we're asked to find, the acceleration after 2 seconds, right, or at the 2-second mark. So I'm just plugging 2 in to my acceleration function here for t. So 24 times 2 squared minus 54 times 2 minus 12. So again, this is 24 times 4, so that's 96. This is 108, and then minus 12. So this is negative 12 and another negative 12. So this is negative 24, overall, and this is going to be meters per second squared. But all I'm entering is the value, right? They have the units there for me already, so I don't have to type that. This is a negative 24. Great. All right, so this is pretty much the same thing. You know, given a position function, asked for the acceleration at 3 seconds. All right, so I'm not going to write all the units. They got the units there, the meters per second squared already. So again, position function given by another polynomial, all right, 2t to the fourth minus 6t cubed minus 7t squared plus 9. Velocity is the first derivative of that, so 8t cubed minus 18t squared minus 14t. And then the acceleration would be the derivative of that, so 24t squared minus 36t minus 14. And we want the acceleration at 3 seconds. All right, so I'm just plugging 3 into this. So it's 24 times 3 squared minus 36 times 3 minus 14. All right, so 3 squared is 9. So that's 180 and 36. So that's 216 for the first term. And 90 and 18, so that's minus 108 for the second term. And then minus 14. So 216 minus 108. That'd be another 10, that'd be 108. Then minus 14 be 94. Positive, positive 94 meters per second squared. Right? But I'm just putting in the number 94. All right, so that objective with just the acceleration function mentioned is done, and now we're back to the only thing left is those ones where we're asked to determine where it's speeding up or slowing down, right? The relationship between velocity and acceleration. So very similar to a problem earlier, some hummingbird flying along a straight line path. Position is given by this polynomial here. Again, non-negative time. So on what time intervals, right? For what times? Now this time it's slowing down. The first two of these was speeding up. This time it's slowing down. But I'm still going to approach it the same way. All right. So positions given by this, negative 1/3 t cubed. It was t cubed divided by 3, but negative 1/3 t cubed plus, and then 7/2 times t squared, or 7t squared over 2 minus 6t plus 2. And this is in yards, these positions. Now they're asking, where is the bird? Slowing down. I've mentioned this way back in the beginning of the video, right? Slowing down means velocity and acceleration have opposite signs, right? It's like you're going against the wind or against the current. You're being slowed. You're moving one way, but the push is the other way, right? So one's positive, one's negative. Opposite signs. So let's look at velocity and acceleration, right? So again, the velocity function, the derivative of the position. So that'd be negative, 1t squared plus 7t minus 6. And then my acceleration function would be the derivative of that, which would be negative 2t plus 7. So I'll do the number lines again. These are time lines, right? These are not by position lines, and we're only focusing on, non-negative times. So again, 0 on the left here. This will be my velocity timeline. This will be my acceleration timeline. Now, if you were to factor, this is a nice factorable one again. I can pull a negative out. That'd be t squared minus 7t plus 6. So this is the opposite of, t minus 1 times t minus 6. So there are 2 times where the velocity is 0. That's at 1 second and 6 seconds, right? So the velocity is 0 at those times. The bird be at rest, pause for an instant at those moments. And then very clearly, when t is 0, velocity is negative, so I have negative velocities up to the 1 second mark, and then you can plug in values in here. There's positive velocities and then negative velocities again. That's only because none of these factors had even powers. You might remember multiplicities and stuff from pre-calc or algebra. So birds moving left, birds moving right, and then left again, right? And it's pausing at the 1 and 6 second mark. All right, now the acceleration, if you were to set this to be 0, subtract 7 divided by negative 2, it'd be 7 halves, right? 3.5. So that's in between 1 and 6, 7 halves. So I'll put that down here, line these up. So again, here's the 1 second mark and 6 second mark as well. But at 7 halves, at 3.5 seconds, the acceleration is 0. And then to the left, when t is 0 here, you have positive accelerations for the first 3.5 seconds. And then beyond 7 halves, you'd have negative acceleration. So again, it's like the wind is blowing to the right in the first 3.5 seconds, and then it turns and starts blowing to the left and pushing the other way for the rest of time. So now you look at these intervals of time, right? Look from 0 to 1, the special numbers that show up in the velocity and acceleration timelines here. From 0 to 1 second, see how they have opposite signs. You're moving left, but the wind's blowing to the right, so you're being slowed. Slowed down. Then from 1 second to 3.5 seconds, velocity and acceleration are both positive, so it's moving to the right and being blown in that direction, blown to the right, going with the wind. So that's speed up. And then from 3.5 seconds to 6 seconds, opposite signs again. So the bird's moving to the right, but now the wind turned left, and so the bird's going against the wind and being slowed again. And finally, the rest of time, beyond 6 seconds here, they're both negative. So it's more speed, right? Speed up. because now the bird's moving left and the wind is blowing to the left as well. So the bird's going with the wind being sped up, if you think of it that way. I like, I know they didn't mention wind in any of these, but I like, again, that's how I like thinking about it, as wind or water or some force that's pulling or pushing you in some direction for acceleration. But yeah, so we want the slowed down ones. Okay, so this bird is being slowed from 0 to 1 second. Again, I'm going to include 0 there because, at 0, they do have opposite signs, velocity and acceleration. So bracket on 0, but not at 1 because, again, velocity is 0. Or, and then there was this other interval from 3.5 to 6, 7/2 to 6, where, at 7/2, I'm going to put parentheses because, again, it's not, acceleration 0 there. It's not positive or negative. And same with 6, the velocity is not positive or negative. So parentheses on those. But here are the intervals I'm going to enter. Those are where the velocity and acceleration have opposite signs. So you're going against the wind. You're being slowed down. So again, bracket 0, comma 1, parentheses. Then it says write it as a union again. So union. And then now you can put 3.5. I'll put the fraction though. 7/2, 3.5, comma 6, parentheses on all of them. Great. All right, so another one here where we're asked, where is this bird that's flying in a straight line path with, this position function given, over what time periods? Is it being slowed down again? Is it slowing? Is it, speed decreasing? Once again, this is where the velocity and acceleration have opposite signs, right? So that way you're moving into the wind, you're moving against it. It's blowing against you, slowing you down. All right, so very similar problem. Hopefully you got the hang of it by now, but practice, practice, practice. So position functions, this polynomial, negative t cubed plus 9t squared minus 24t plus 4. Once again, they mention non-negative times, so don't worry about negative time. Velocity, let's look at the velocity. It's negative 3t squared plus 18t minus 24. And then the acceleration would be the derivative of that, right? Negative 6t plus 18. I'll make my two timelines again. So again, one timeline starting at 0, right, for the velocity. And then directly beneath that, another timeline, right, for the acceleration. Again, starting at 0, just trying to line things up nicely. This factors nicely, right? This is negative 3 times t squared minus 6t plus 8. So this is negative 3 times t minus 2 times t minus 4. So 2 and 4 seconds. So at the 2-second mark and 4-second, 2 seconds into the trip, into the flight, it pauses at rest. And then 4 seconds into the trip, it's also paused, right? So velocity is 0. And then, at 0, you got negative. So you got negative velocities here. And once again, none of these factors are having, none of these solutions have a multiplicity that's even. So they all have odd multiplicities. So you will get this alternating sign thing. It's positive between 2 and 4, and then you'll have negative velocities to the right of 4. So the bird's flying left for the first 2 seconds, flying to the right for the next 2 seconds, and then after 4 seconds, it's flying to the left forever. Then the acceleration, negative 6t plus 18 would be 0 at 3 seconds. So 3 seconds is here, so I'll mark down 3 and all the special numbers down here, 2 and 4 from the velocity one. But at 3 seconds, acceleration is 0. So there's, like no wind for an instant. And then, when t is 0, this is a positive acceleration. and then negative to the right of 3. If you plug in a value bigger than 3, that's negative. All right, so now we got all the special values from velocity and acceleration down here, and let's just take a look at between each of them. So from 0 to 2 seconds, see how the velocity is negative, but the acceleration is positive. So that's, moving to the left, but the wind's blowing to the right. You're going against the wind. That's slowing you down. Then from 2 to 3 seconds, they're both positive, so you're going to the right. The bird's flying to the right and the wind's blowing to the right, so it's being sped up. It's going with the wind. And then from 3 to 4 seconds, positive velocity, negative acceleration, so the bird's moving to the right, but the wind starts blowing left against the, so the bird's moving against the wind, being slowed down. And then from 4 seconds onward, negative, negative, so it's being sped up. It's moving left, the wind's blowing left, you're going with the wind, so you're getting faster, you're getting sped up. But we want the slowed down ones, right? So the intervals are from 0 to 2. Again, the bracket on 0, because, it has opposite signs. The velocity and acceleration have opposite signs at 0. Parentheses on the 2, union, and then the other interval where you're slowing down here is from 3 to 4 seconds. Parentheses on those. So this is what I'm going to enter. All right, between 0 and 2 seconds and 3 and 4 seconds. This hummingbird will be, slowing down. So you bracket 0, comma 2. Then they say right as a union, so no comma there, just the union symbol. 3, comma 4. All right. And don't forget to read through your answer explanations. I think that should be it. Yeah. All right, great. So, again, this is a preview of this assignment. Hopefully, watching me go through these here will help you in some way when you work on them on your own. And thank you very much for watching.